Hello, in this video we're going to take a quick overview of section 5.2, the double integrals over general regions. So in studying general regions, we're going to take a look at the different types of regions that we're going to integrate over, and then we're going to establish some sort of order of integration. And then we'll take that to study some improper integrals. First, the type 1 and type 2 regions. So a more general region just means it's not a rectangular region. And if it's not a rectangular region, then when you integrate with respect to one of the variables, you're going to have to put in non-constant values or functions inside for those limits. For example, a type 1 region, we'll say, is integrating with respect to y first. And your region then can be seen as an area that can be found by looking at the different y functions. So y is a function of x. So in these examples, we're integrating with respect to y first, and you can see the difference arrows going up and down within the region. Where it hits on the bottom, it hits the bottom function. That's going to be your bottom limit, and then on top it hits the upper function. And the key here is that the x values would just run from a to b. So imagine that slicing idea where we're going to get slices that's going to be parallel to the y-axis, and for each of those slices we'll take the area that's going to be covered between G1 and G2, G1 of x and G2 of x, and so we'll set those as the limits of integration. A type 2 region is just going the opposite way. So we would integrate with respect to x first, and we would think about a line parallel to the x-axis, and we would imagine as we go through that line we would hit the area, the region, with some x is equal to y1 of h1 of x function. So x is equal to h1 of x function, and then it'll be in the region until you get out of the x is equal to h2 of y function. And so in integrating with respect to x first, you will have x limits that would be functions of y. And then again, if you take a look at the limits with respect to y, it's just going to be from c to d, it's going to be constants. So that's going to be one of our big themes. We're going to take a look at the limits of these things as constants. The outer limits of these integrals will be constants. So if we keep that in mind, then we'll have more success in setting up these integrals. So now that we have these ideas of type 1 and type 2 regions, we're going to construct our iterated integral by looking at the integral with respect to y first in the first example over here, where the y limits go from g1 of x to g2 of x, and then with respect to x, where x goes from a to b, versus the second integral where we integrate with respect to x first, and then we're going to have functions of y, h1 of y and h2 of y, and then when we integrate with respect to y, they'll be constants. So we can kind of view an example like this where we have a parabola, y is equal to x, and we have the x-axis, or y is equal to 0, and then it looks like x is equal to 1 is going to be our ending point. And if we integrate this with respect to y first, this is a type 1, if we treat it as if it was a type 1 region. We can imagine this line going up and down this axis, or this line that we drew, and you're going to enter the region where where y is equal to 0, and then you're going to exit the region where y is equal to x squared. And so in setting up your double integral, I'd like to set up a set of inequalities that say I'm going to integrate with respect to y first, going from 0 to x squared. And then once I do that, that's going to go inside of my iterated integral, the inner integral, and then the outer integral will have constant limits, x going from 0 to 1. Now we could take the same region and integrate with respect to x first. And so this turns out to not only be a type 1 region, but can also be seen as a type 2 region. And if we integrate with respect to x first, we would draw a line parallel to the x-axis, and we would enter through the region at this graph, y is equal to x squared. But then you want to view it as a function of y, so you're going to say x is equal to the square root of y, and then you're going to be inside of that function until you get out when x is equal to 1. And once you establish your x limits as the inner integral limits, then your outer limits x will just go from 0 to 1. So here's the setup. Draw a line parallel to the x-axis. You will enter the region when x is equal to square root of y, and exit the region when x is equal to 1. And then your outer limits go from, your y goes from 0 to 1. Okay, and so we get used to doing a whole bunch of integrals. We're going to identify them as type 1, type 2 regions. Sometimes they can be both, so you can do either integration order, or sometimes they are strictly going to be a type 1 region, so you're forced to use one of the orders of integration. Once we get these ideas of the order of integration going, then we're going to take a look at just briefly some improper integrals. And an example of an improper integral would be like a bell-shaped curve or something like that, where your region could be the whole xy plane, and then you can just extend your region. And so we're going to do this extension by looking at finitely stopping at some arbitrary value of b or d for x and y, and then letting that go off to infinity. And so that's the idea behind improper integrals. We'll do a couple of problems just to get us kind of going with that, but we'll be focusing more on our finite friends in calculating these double integrals. All right, I hope we're ready.